Hello Stats class, this is the notes for 3.2b, which is about residuals and calculating the line of fit. We've been using the line of fit without actually calculating it, and I'm going to show you how to do those calculations today. So first of all, residuals are about measuring how well a line fits the data. And I'm going to have you draw a large scatter plot. I'm saying large because we're going to draw all over it. So give me a moderate positive trend. I don't care if your points are exactly the same as mine or not. And I want to point out that you could draw a lot of different lines of fit on here. You could draw one that's too low or too high, like in my song, or too flat or too steep. And there is a best line of fit that's about right here. I'm just going to estimate it for now. That goes through the points and is evenly balanced with points above it and below it and following the general trend. So that's the first thing. We're going to learn how to calculate the best possible line. And in order to do that, let's talk about some of what we've already talked about, but let's talk about residuals first. So residuals are how far each point is off the line vertically. So pick a point and draw that little vertical line. That is called the residual. I want to remind you that this point here is the actual value, which is x comma y. And this point right here is the predicted value based on the line, which is x and y hat. So y hat is the point that's on the line, and y is the actual data point. And the distance between those points is called the residual. The residual is the vertical distance off the line. This is why I asked you to make your plot big so you could have plenty of room to write this stuff. So residual is y minus y hat, and it is that vertical distance from the point to the line. Actual minus predicted. Some people remember it by doing AP, actual minus predicted. Let's write that over here. With the actual first. We've actually seen that before when we did standard deviation, and when we did deviations, we did x minus the mean, which was the actual x value minus the mean, which is kind of like a prediction of what your best guess is for the x values. So that same thing shows up in multiple scenarios, and this is one of them. Actual minus predicted, y minus y hat. I'll write it bigger over here just to make sure. That's how you find the residual. So if you look at these points, each one of them has a residual, and I'm going to draw a whole lot of little vertical lines like this. You'll notice that if the point is on the line like this one, actual minus predicted is just 0, so this has a residual of 0. If you don't have any points on the line, go ahead and create one so you can label it. And you'll also notice that some points are below the line and some are above. This one has a positive residual because the actual is bigger than the predicted. But if it's below the line like this, it would be a negative residual. So pick one that's negative and label that. All right, so what we're going to do is talk about, to get the best line of fit, we want to minimize those residuals. We want them to be as small as possible. In fact, what we do mathematically is we try to minimize the squares of the residuals, and you can visualize this by drawing the little squares. We want the sum of these squares to be as small as possible. Now, this one's a 0, so I don't have to draw a square on it, right? But all of those squares, if you move the line around, the squares will change a little bit. And the idea is you move the line until it is just right, which is the smallest possible sum of squares. And that is called the least squares regression line, which is what we're learning how to do. It's often called the LSRL. I may ask you later what LSRL stands for, and hopefully you would remember that it's least squares regression line. If I'm too lazy to write this, this is what I write instead. What do you know? It minimizes the sum of the squares of the residuals. Now, there is a way to mathematically prove that, and I may make another video that shows that. It's kind of long and is only interesting to some people. So if I make a separate video, it'll be optional, showing you the proof of why this thing I'm about to show you does actually minimize that sum. But for right now, you're going to just trust me, and I'm going to show you how to calculate it, which is the how, not the why. And if you don't trust me, then watch the proof video. Calculations to find the best fit line. And best fit in this case is least squares regression line. I will tell you why it's called regression later also, not quite yet. So the first thing you need to know is first part is kind of common sense. Remember we talked about z-scores to find the correlation, and we talked about the x-bar line. So like pick a spot that looks like it's about in the middle of your x's, and let's label that as x-bar, which is the mean x value. And think about if you have a data value that has the average x, then wouldn't you expect it to also have the average y? That seems logical to me. This point where this meets the line is the mean of y. So make sure that you pass through the line at that point, and that's y bar. Y bar is the mean y value, and it makes sense that the best fit line ought to pass through that point. So in other words, if the x value is average, then your prediction for the y value would also be average compared to the rest of the data. So the least squares regression line always passes through that point. X bar, y bar, which is the mean x and the mean y. Sometimes it's called the point of means, or the centroid is the official name for it. You don't have to write that down unless you want to. But the point of means, oh, maybe I did write it down last year, so okay, fine. I'll write it. The point of means, point of averages, or it's sometimes called the centroid. If you like the geometric approach, imagine taking a piece of cardboard or something and putting weights at all of these spots where the points are. And then if you tried to balance the cardboard on the end of a pencil or something, that's the balance point. That's the place where it would balance both in the x direction and in the y direction. So that's why it's called the centroid. So that's kind of a common sense thing. I'm not going to prove that to you, but I'm going to say we're going to use that in a minute. The second thing you need to know is that the slope of your regression line, which remember, we're using our book's format, which is not mx plus b, it's a plus bx. So in this case, the slope is b. I wanted to remind you of that. The slope formula, I'm just going to give you the formula and then I'll talk a little bit about why it makes sense. Slope formula is based on the correlation, because positive correlation means positive slope, but it's not just the same as the correlation. Obviously, it also depends on the scale on the x-axis and the y-axis. So you take the correlation and you multiply it by sy over sx. And I'll put a box around that, and then I'll talk about it a little bit more. So this is my estimated slope. We'll talk later about why I said estimated. There's a lot of stuff that I'm not going to tell you today because it'd be too much. But anyway, this is the correlation, which you already know can be calculated by finding z-scores and multiplying them together and all that. This is the standard deviation of the y's. And this is the standard deviation of the x's. And this formula makes a lot of sense to me because this piece right here looks really familiar to me. Where in your life have you seen something about y divided by something about x? And if we were in class, I would be asking you to tell me this. And you would, I hope, say, well, that kind of looks like rise over run. Remember rise over run from Algebra 1? And then I hope you've done it a lot more recently than that. Rise over run is basically where this formula comes from. And then, of course, in the proof video, I'll show you more about why this makes sense. But rise over run times the correlation, that is what you need to do to find the slope. All right? And then once you find the slope, then hopefully you remember this from Algebra 1. So I'm going to remind you of point-slope form. If you know a point and a slope, you can find the equation of the line. So I'm going to write it out the way it looks in Algebra 1, and then I'm going to change it to what it looks like in statistics. So in Algebra 1, we do it this way, where x1 and y1 are a point that we know, and m is the slope. So we have our slope, we have a given point, and I hope that looks familiar to you. Like I said, in statistics, we replace a lot of this stuff with different notation. So here's the statistics version of that same formula. We're trying to get an equation for y hat, so I'm going to call this first one y hat, not y. Y1 and x1 are this point that we know it goes through, so that's y bar and x bar. And then we're going to call the slope b instead of m. That is the official formula for finding that. And remember that b could be replaced by the r times sy over sx. That makes it look even more statistical. So this piece is the slope that I just told you how to find. This is the point of averages, or the point of means, that it always goes through. Now, you don't have to use this form. Obviously, I could simplify this form and get it to look a lot better than that. So let's do a little bit of algebra. I could take my slope, which actually I'm going to go back to calling it b. I think that's easier, and I'm going to distribute the slope. So I've got y hat minus y bar equals bx minus bx bar. If I am trying to find, if I'm trying to get the equation of my line, I would probably want to add y bar to both sides. Y hat equals bx plus, let's put this one first because it looks nicer, y bar minus bx bar. And I want to remind you that these are just numbers. X bar and y bar are averages that you could find from the data. B is the slope, which we just learned how to find using this rsy over sx thing, which also you could calculate from the data. This piece is a number that is the y-intercept. And then this is my slope and my x value. And I guess we normally would put this first. The y-intercept is officially called a, and so what this is telling me is that I could find a by doing y bar bx bar. And once again, my computer fell asleep. Oh, I caught it in time this time. Good. All right, so this is the official y-intercept formula, which, by the way, on the formula sheet that you get when you're doing the AP test, they give you this formula and this formula, which is kind of nice. Most of the time, we're not going to use these formulas because the calculator can take a list of x's and a list of y's and do this automatically. But some problems on both the AP test and in your homework might give you just the information you need to use these formulas. So I want to do an example of that. So let's go back to the used cars data. We actually already know what the line of fit is on this, but let's pretend that we don't. Let's pretend that we're just given this information. Remember that X was the mileage of the car in thousands, and Y is the price, which means Y hat is the predicted price. We talked about that the other day. If I give you X bar and SX and Y bar and SY, wasn't that nice of me to calculate all that for you? Amazing. And if I gave you R, that is enough information for you to find the equation of the least squares line. So that's what I wanted to do one example of. Sometimes in the book and on the AP test, they give you just this information instead of the list of data. And they say, find the equation. Let's do that. So we're going to find A and B to get our equation of the least squares line. Least squares regression line. I really want you to get used to this abbreviation so I can keep writing it and not have to say every time what it is. I know I'm being lazy. That's okay. So according to what I said up there, we need to know B to find A, so let's find B first. B is our SY over SX. I have that one memorized. This one I always have to rederive. I do not have this one memorized. It's funny. But this one is easy to memorize because Y over X and then multiply by the correlation. And so I'm just going to plug in the numbers that I need. I've got R is negative 0.874. That negative is how we're going to make sure that the slope is negative like it should be, because remember the price goes down as the mileage goes up. And then I'm going to do my SY over SX. It's really important that you get the right ones. We'll put the Y on top. The Y's rise to the top and the X's are on the bottom. That's the run. And don't use the means for this. Use the standard deviations. When you plug all that in your calculator, you should get negative 85.54, which, by the way, is the slope that we had the other day when we did this example when we were just given the equation. Then I'm going to find A. I'm going to use this, which is Y bar minus BX bar. So Y bar is 14,425 minus the slope. We just found that, right? So minus a negative 85.54. That's important that it's minus a negative, because if you do minus a positive, you'll get it wrong. And then I need the X bar, which is 50.5. So if you type all that in your calculator, this becomes a positive, and you get something bigger than the 14,425, which makes sense. The y-intercept ought to be, if it's negative, the y-intercept ought to be bigger than your y bar. This is your A up here, y-intercept. So it does come out bigger. It's 18,744.77. All right, and then that gives us our equation, which looks like this. And I'm going to do it the way the book does it, which is putting A first, 18,744.77. I actually really like putting the y-intercept first. I've had some algebra books that do that. It's like you start there, and then you go down by how much. So like, let's start with the thing that you start with. It makes sense. There's another reason it makes sense, but I'll tell you that later when we get to that. So that is my equation that I just found. Remember that this is our estimated price for 0 miles. And this is our estimated decrease in price whenever the miles goes up 1,000. So that is how you calculate the best line of fit. And I'm going to stop there. Like I said, there's going to be probably another video proving that these formulas actually work if you're interested in that. But that is all you need to know, is how to use the formulas for now. And I can't find the stop button. So awkward.